Hello everyone, it's May 12th. Didn't do it yesterday because I was working on the app. We had some issues. Seems like different Android phones has different rules on the positioning of the bars, the status bar, the bottom bar, the window, and also the height. Like what does the prop top means? I'm not 100% sure, but so far what I see is different phones has different rules. Because I was running the app on my Samsung, and it shows one way, and I run it on an emulator for Pixel, and it shows a different way. So the two, like the same code, will have different demonstration, different layout when you run the app. So this never happens with iPhone because it's I guess it's very consistent how it is. But in Android, yeah, if you think about it, it is different because you have different companies. They might tweak the phone differently. So it probably means we need to write code in such a way that different phones have different specifications of how the things work. We'll figure it out. We'll figure it out. So we'll spend some time to figure that out. Today went to the DMV to get a new driver's license. Have to pass a driver knowledge test. Didn't read the handbook. Just go right into. I read 20, 30 pages and went right through the thing, and it was terrible. Failed. Failed the first shot, and I had to take a second one in order to pass it. But all's well. We assembled a bench, so that's good, and everything else will arrive in a few days. I think the bench will arrive on Saturday. No, the squat rail will arrive on Saturday, and the bar will arrive in 4 days. So sometime next Monday. All right, let's go right into it. So today, today, the problem is permutations number 2. It's an old problem. What do we want? We want a collection of numbers that might contain duplicates. Return all possible unique permutations. I remember this. Unique permutation, that's the difficulty. It's to make it unique. One way we can do, just to make it a regular permutation problem, and then we just store them in a set. Yeah, definitely that's one way to think about it. Is there another way? Well, how would you usually do permutations? Well, you set aside like it's a recursion, right? So 1, 1, 2, we say 1 set aside and 1, 2, we're gonna do all the permutations. We say we do all the unique permutation of that, and then we try to add 1 to every single spot. But now we have an issue because we can have duplicates. I remember there's a way to deal with a duplicate. I don't remember. What is the way to deal with duplicates? Duplicate, duplicate, duplicate. We can say, all right, let's write a stupid way first, okay? And then we can handle whatever else we want to do. Yeah, I think I didn't do 11th. Is it 12th? Hold on. Let me make it better. We don't have a chair. We have a chair, we don't have a table, so makeshift table. There we go. That's better. So this one is done. Yeah, this one's the timeout. So if we have time, we want to take a look at that one for sure. But this, we need a set. Okay, def permute. we need a index, right? Ooh. Yeah, we do return list of list. And when the rest equals a set. Okay, so what do? We do if index equals len_nums, turn this. Okay. Otherwise, we take it and then we get a result. And then for everything, you know what? Let's do better. Let's do this. We're going to return nums index. All right, that's just the last one. And then for every one, we're just going to say for rest equals this. For p permute index plus 1. Right, for each one, we're going to go just to the front, the middle, at the end. Right, we do that. So how do we do that? When I say temp equals, let's say, p. Ooh, hold on. For I in range, len p. Right? So len p, so from 0 should be p to I plus nums index plus p I towards the end. What's the temp? Of course, not temp, current. Right, so for current, and then the rest are add tuple current. Right, so return rest. And then we're gonna call permute 0. Ooh, nope. Yes, we'll just do that. And then, how do we remove? So this one give me permutation, right? So we can say set tuple p for p in this, and then sp in this, list sp, turn into a list. Maybe this won't be fine. Return this thing. I believe this shall be right. Okay, let's try it. Permutation, unique nums. That is not right. Wait. If I do 1, right? So we say 1, 2, do permutation. Permute 0, right? And then immediately I say permute 1. And permute 1, immediately I say permute 2. Permute 2 will equal to this. So we return nums inside as a 2. And then in permute 1, so 2, we get a 2 out. Right? Get a 2 out. And then there's 1, so I becomes 0. Okay, to be len plus 1. Yeah, that looks more likely. Let's say sorted res equals sorted answer. Yeah, this one will be right. And of course we don't need this one either. Try it. Maybe we can do it, I don't know. What if I just return a set? Does it still work? You're not supposed to return a set, but I am returning a set, so it still works. Okay, so this is the naive solution. So this is the naive solution using a set to identify duplicates. So there definitely is a way to do duplicates without going through all this trouble. How? Let's get the unique values out, right? Let's say if we have 1, 1, 2, 2, 3, 3, this is 1, 2, 3, right? These are unique values. So we can have unique values doing permutation. We can get all of those. And then, I don't know. I don't have so many different solutions I had in the past. gotta be a way. Yeah, I think these two solutions are the same. And these are the easier one. I don't know what the easier one is. Mute. To check for duplicate while you're going through. So if I pick the first one in this spot, right? And then if we have a different thing, I don't know. What are the solutions? Too lazy. What are the ways without? This is the same. This is the same solution. Backtracking. Backtracking. Interesting. What does this mean? Backtracking. I think what it means is as you're going through, so for each position, you can choose. Okay, so for each position, you have all these choices, and you choose, I want to put this. Okay, so next position, you can put this. Next position, well, you cannot put, then you can put this. You can put this. Okay, so now we're done. Right, so go back. How do you prevent duplicates? Because of the counting. I said if this one in the front, then we have this one left, right? It will not happen again, because if you want to happen again, it always starts from the front. And I already put this in the front. I see. It is counter. So backtracking, so every single step we do one value. Do one value, do one value, do one value, and that's it. And then we go through everything, all the remaining. And the reason that's not going to, because after we use every value, the state changes. So that's why it's not going to repeat itself, because the counter is the state, right? The counter is the state. And then whenever we put down a value, the state is unique. It's a unique state inside a counter. So we will not hit. Yeah, because the state of the counter for each time you put in is different. For each time you put in is different. If the state of the counter at each time you put in is different, it's not possible to generate two sequences that's exactly the same. Because they have two sequences exactly the same, we require two sequences, right? Like they must have the same state for the two sequences to be exactly the same. But if you use a counter, and each time you put in, you decrement the counter. So each state is different. You can't even arrive with the same state. Each state only has like one chance. backtracking. It's worth writing out the backtracking code. So this is the backtracking. Directly producing unique permutations, because each time a number is put down in a permute, the state of the counter of all numbers is always unique. Thus, it is not possible to have two identical sequences of numbers. So we're doing the counter. Okay. And then we basically just say backtrack. Right? Backtrack what? We can have n equals sums backtrack current. A list of int. Don't return anything. And then rest. Right, let's say if len current is equal to n rest append current, else, then we add a new one. Then we say for key encounter keys. Why not key value items? If v current dot append key current key minus equal 1 backtrack current dot pop current key plus equal 1. So all we need to do is call backtrack this, and now we need to return rest. Index out of range. Oh, it's not current. Counter. Yeah, this one will be faster. Okay. Done. Oh, let's go back to this. Yeah, I'm gonna check the hint. Hint 1. The height. Oh, I didn't see that. Come on, man. Read the question. The height is at most 100. Ah. Huh. Okay. Okay. That's enough. I think. Yeah, the height. Oh my god. So we just need to do binary search, right? So we know where they are, and then we So for x, we need a binary search, right? So for x with binary search, so we will end up at certain points, right? At this point. At a point, now we know that it's in between the two, okay? And then we know it can belong to, and then what? Then we want to find out how many of them have hold on. So we want to find out how many of them. Yeah, so let's say I have like 10,000 rectangles, right? But the height is only 100 different heights, right? I only have 100 different heights. So among those 100 different heights, I cannot iterate through all of them, because that takes too long. It takes too much time. Heights. All right, let's say for heights, I have this height, I have 100 height. So the first height, I have a bunch. The second height, I have a bunch. So based on height, we sort based on height. So we have height with this, and then we need to create. So for each height, so we sort based on height. Okay, we sort based on height, and then based on height, and then based on x, right? So then, because it's based on height, what I want is from this height to next height, right? So we have the minimum height. This is the minimum height. Everything is smaller than this. And then what's the next height? Right, and then we have next height. And each height each height. So I will have duplicates on all those heights, right? We'll have duplicates on all those heights. So each height can have multiple. So basically, when I create an array, there's 1 to 100, right? 1 to 100. So we basically say height equals 1. What are height equals 1? Height equals 2. What are height equals 2? Height equals 3. What are height equals 3? Okay, so once that is done, and then my value pass in. Okay, so I don't even have to find, because that's a list. So my height, the point's height. So what we want is the point's height and everything above it. Okay, so from point's height and everything above it, for each one of them, now we're gonna do a binary search. Okay, so it'll be like this. When I say with, let's call it, what should we call it? Width on height. Table. Table. All right, so it's going to be this for this in range. Should we sort it? If we sort rectangles based on the height, right? And then we can go, yeah, I think I can do this. I can say rectangles are sort, okay? Key equals lambda rec, and then return rec 0. No, rec 1, rec 0. Right, because of that, it was sort on that first and then on the other one later. And then we can say table tab equal to for this range 101, because 1 to 100, right? And then we say for length and height in rectangles. Let's sort it. Say tab h dot append l. Okay. Once it's done, right? Once it's done, then we're gonna say given points. So a bunch of points. So we're gonna say heights for equals to Nah, I don't like that. I don't like that. Just I want to be at this. Default dict. Okay. So this will be a default dict, a list, and tab yes. The height's gonna be tab.keys. Of course, turn into a list. Okay, so index y, bisect left, heights. Y's. No, heights. Then what? So heights and point. Hold on, for x, y, and points y. Okay. So we know everything above the points is what we want, right? And then we just count. And then, because bisect left, so basically just go with index y, right? And then we say for j in range from index y to len heights, right? So for all of them, for each of them, we're gonna do rest equals this, and then rest append 0, and say rest -1 plus equal to plus equal to what? We're gonna do bisect left tab heights right index y. That's all the x's. So binary search this with x. Okay, so I'm gonna get this, and then we're just gonna use as the index. So I'm gonna say len heights index y minus this. Right? Think about it. So 0, 1, 2, 0, 1, 3 minus 1 is 2. Yeah. So we're gonna do this, blah blah blah. Once we're done, now we can return result. All right, give it a shot. Int has no len. Oh, of course it's not heights, it's tab. It's tab heights index y. Okay. Hold on, I don't like heights. YS. I don't like index Y. YI. Okay, the first one is not right. Let's see what happened. Nah, don't worry. Let's print tab. Okay, so 2, 3, 5. 2, 3, 5. 2 will have 1, 3 have 2, 5 have 2. Okay, so the first one coming in is 2, 1. Okay, 2, 1. So 2, 1 come in, it's gonna be 3 or 5, right? 3 or 5. Okay, I can actually print. Let's print yi as well. So, oh, wait, hold a sec. So coming in 2, 1, x, y, right? X and y. So your y to search, my bad, y to search is 1, right? And I have this, this, this. Y search is 1. So it's 0, because y is 1, so it's 0, okay? So I'm going to go from 0 to the len ys. That's correct, because we can hit every single one. And then be len tab ys. Oh, it's probably not yi. This should be j, right? There we go. It's j. All right, this is right. All we need is a little bit hint, and that hint actually helps a lot. Do we there? I want to double check. From the last time I do this, the time take us 8 seconds. Yep, this one's good. Yep, so we did take a hint. We have to take a hint. And the hint is there are at most 100 unique y values for the rectangles. So yeah, I didn't read the question specification carefully. Since there are so few y's, it is possible to list all x's for each y in ascending order. Then we binary search on y first to locate, to identify, right, which which y's are appropriate, are possible, are likely to hold a point. And we iterate through all lists of x's of each y and use another binary search to see how many x's are appropriate, are able to hold the point. So runtime, well, let n be the length of rectangles, m be the length of points, and we have O n log n, right, plus m points times m times log n, well, actually log 100 plus, so 1, right, this is log 1, log 1, this is, we'll call it log n, so m log n. Yeah, see the constraints. Each height to the lines. Okay, that's it. So we just solved this one. We still have one more thing unsolved. I'll handle that some other time. Alright, that'll be it. Not too bad. I'll see you guys tomorrow. No, I'll see you guys tonight for tomorrow's challenge. Adios.